Good morning, students. I am Navdeep Dhaliwal, faculty of Arya College of Engineering and IT, Electronics and Communication Department. In this session, I will be going to explain delay line canceller in radar. So, how we use delay line canceller in radar and why do we use delay line canceller in radar? So, to explain that, these are my session outlines. First I will explain basic of delay line canceller, then I will explain block diagram. Then after, based on block diagram, we will see how delay line canceller functions, and in that what is blind speed of object and how to avoid blind speed of object in radar. So that is what I will be explaining in this session. So let us begin this session with basics of delay line canceller. So when we talk about delay line canceller, why we use it and where do we use it? So delay line canceller basically used in MTI radar system. So delay line canceller that is being used in MTI radar system, basically it is functioning as a filter where we filter low frequency. So it is being utilized as a filter to filter out low frequency. It will eliminates low frequency clutter in received signal at radar. So this delay line canceller that will be eliminating low frequency components, that is even referred as clutter in radar, so that what we cancel out by using delay line canceller, and because of delay line canceller it improves resolution of object identification. So usually when we have moving target indicator, we connect delay line canceller just before of display, and by having this we can have improved resolution of object identification. So this is what about basics of delay line canceller. Now let us move further. Block diagram. Here we have received signal of radar at the input, and that is what provide it with delay line, and that delay line is based on pulse repetition frequency. So 1 by pulse repetition frequency amount of delayed, and we provide, and that is what we subtract with original signal. So ultimately we will be having resultant signal which is having elimination of clutter low frequency components. For example, if I say we have signal V1 and that signal is given to the subtractor, and if I say we have signal which is what delayed one, that is V2, so at the output of subtractor, if signal is V, that V has to be V2 minus V1. So based on subtraction, one is actual signal and one is delayed signal. We will be able to eliminate clutter which is received by that radar, and that is unwanted signal. Clutter is noise signal, that is unwanted signal. So that is what we eliminated by this delay line canceller, and that absolute value that we give it to display to identify object position as well as motion. So let us try to understand what will happen with this V, which is what output of this delay line canceller. So if I consider I have a signal that is V1 and that is k sine 2 pi ft minus phi 0. See here Fd is pulse repetition frequency and here we have V2 that is delayed one. So V2 is k sine 2 pi Fd t minus capital T minus phi 0. So that is what V2 signal. Output will be V, that is V1 minus V2. So here output that is V is equal to V1 minus V2. So we can see in this image the value of V is 2k sine pi fdt cos 2 pi fd small t minus capital T divided by 2 minus phi 0. So my signal is 2k sine 2 pi f dt. This is actually amplitude or one can say response. So if I plot it with respect to frequency, then we will be getting that response that is like as shown in figure. So this is what the basic response that one can identify. So here in the figure maximum amplitude is 2. So in this basic diagram one can observe we are delivered to eliminate low frequency noise which is ground clutter. So low frequency is an area near around where frequency and amplitude is minimum. So we can see here magnitude is minimum. So here we have elimination of low frequency noise, but at every minimum value of magnitude in continuous frequency cycle at 1 by t, 2 by t, 3 by t, 4 by t and 5 by t, here also some frequencies are removed. So at each minimum magnitude nulls are there and that are removed. Now I will explain you term. This is what blind speed. So when we talk about object in motion, and here we use this delay line canceller with MTI moving target indicator. So if object is moving, it is drift frequency FD, that is 2VR divided by lambda. Here VR is relative velocity, and if it is Fd is equal to n divided by capital T, where n is multiple number, if it is n by t, so in that case we can say it is n multiplied by fp. In this drift frequency of object, that is exactly super multiple of pulse repetition frequency. In that case, as response is 0, we don't be able to identify what is motion of object. So at this frequency we cannot identify motion of object. So at a, at a frequency at which drift frequency f is equal to nfp, we can say at a frequency at which drift frequency is equal to super multiple of pulse repetition frequency, we cannot identify object motion. So why we cannot identify motion. Reason is response is null. So this is what blind speed. Now, how to avoid blind speed? What we can do is we can cascade multiple delay line canceller before we give signal to display. So if you connect multiple delay line canceller in cascaded form, then we can able to provide that resolution which is not be happening by single graph. So this is how we can connect delay line canceller in cascaded form to avoid blind speed of object.